discussion about entanglement, and we will focus on what we can, so some kind of examples in which we will, just 1 second, to avoid any problem. And we will discuss possible examples in which we will use entanglement as a resource to realize some kind of process. So the main example which we will focus, it will be the quantum teleportation, which the idea of quantum teleportation that sometimes is not completely clear is that we want to bring a state from Alice, that is one of the so we want to bring to teleport a state from Alice, that the sender of the state, to Bob, that is the receiver of the state. The idea is that neither Alice nor Bob does not know the state. That is the important thing, because obviously if they know the state, they can communicate classically all the parameters that they want, and then Bob can reconstruct the state without any problem. But the idea is that Alice and Bob, both of two, does not know the state. In some way, you can consider Alice and Bob like sort of postmen, so people that work in two different post office, and then one of you want to send his one quantum state to one of his friends in another city. So he brings the state to Alice, that is one of the postmen here in Palermo. Then he do whatever he has to do, that now we will illustrate, and then send the file to Bob. As a postman, since the postman normally does not read your email, your mail, again, also Alice and Bob does not have to know what is the state that you want to report. So let us start to put an example. So, so Alice and Bob are in two different well-separated space, in well-separated cities, to make an example, and they share a state that is, in this example, is the maximum entangled state, like 0 plus. So this means that this state here is on a qubit that can be assessed by measurement or whatever, or they can be modified by the action of Alice, and this state here, the action of. So at the beginning of the process, someone brings to Alice another state in which is written the information that you want to teleport. So at the beginning, so the state, the initial state, here becomes alpha plus alpha. Zero plus beta 1 tensor product 1 square root of 2. Okay, I removed the suffix plus. So we can extend this one, we obtain 1 square root of 2, alpha 0, 0, 0 plus alpha 0, 1, 1 beta 1, 0, 0 plus beta. So, where of these three indexes, each one refers to a qubit. Two of them, the first two, can be observed, can be acted on from Alice, and the third one. So now the idea is to make so Now what happens? Now Alice decides to make a measure. So they decide in what we said before to realize a CPTP is a local operation and classical communication measure. So it acts only locally, only on the degree of freedom of Alice. And this act as making a measurement. What kind of measurement? A measurement that have this particular situation in which the four projector that are that individuate the observable are the four best state. Yeah, sorry, 1, 2, 3, 4. And now when we have here, we have 1 over square root of 2, 0, 0, plus or minus 1. So the idea is that the important point, the key point of this measure is that the result, so the vector in which the measure projects the state is one of four different maximal entangled states. All of the states that we see here are maximal entangled. So at the beginning, we have a maximal entangled state between the second and the third qubit. So 1 qubit from Alice and 1 qubit from Bob. Instead, now we want to make a measure that involves the 2 qubit of Alice. So we want to project on an entangled state, not on the state between Alice and Bob, but the two qubits of Alice. So at this point, we can, from this situation, so it seems easy to see from this relation that we can to make all the step further. It's easy to write down that 0, 0 can be written as a linear combination of plus, plus, minus 1, 1 is 1 square root of 2 by plus, minus, minus, and yeah, 1, 0, 1 square root of 2 by plus, plus, by minus. And then 0, 1 is exactly the same, but with the minus. So using these four identities, we can rewrite the state here in this way. That is the state C is equal to 1 over 2. So we have alpha psi plus minus 0. Then alpha is 0, 1. Psi plus minus. This is this one. Plus theta 1, 0. Oops. Plus, minus, minus, beta, plus, minus, minus. So with it's okay. So again, let us. So now we can rearrange the state. So we can write down here psi as 1/2 pi plus. It is alpha 0 plus. Oh, sorry. Yeah, there was a. This was 0, 1, 0, 1 plus beta 1 plus 4 phi minus obtain alpha 0 minus beta 1 plus psi plus psi plus alpha 1 plus beta 0 plus psi minus it is alpha alpha 1 minus beta 0. Okay. So okay, we have these long series of steps that, but the steps are very useful because allow us to evaluate easily what happens when we make the different measurements. So as you see, we have an observable, we make the measure, and the measure can project on psi plus, psi minus, phi plus, phi minus. Now, what happens? So when we have on phi plus, on Alice, the state that is realized on Bob is exactly the initial state that we wanted to send to Bob. So it's perfect, it's already done. So if you want to look at this, say, okay, we ended. But unfortunately, this happened only when we observe this state. So the eigen, to be honest, when we observe the eigenvalues associated with this state. When we have phi minus, it's something, as you can see, it seems something similar. It's not exactly the state that we have designed before, but in some ways related to. So we have the same, we have not the same kind of information, but a related level of information, because the state still depends on alpha. And the same stuff happens for phi plus and phi minus. So the point is that if we, so this point that seems a problem, to be honest, instead is something that really saves the approach of quantum teleportation. Because imagine that for 1 second that in all the cases the state realized on Bob was exactly this state, the state I want to send. In this case, I finished. I made my job. But in this case, I transmit the information with infinite speed, because no matter what is the distance between Alice and Bob, immediately, as soon as Alice makes a measurement, immediately he sends the information to Bob. This is completely crazy because we know that information has a finite speed to travel. So the point is that, okay, now let's see where instead these things save the relativity. Is that in this moment, Alice made the measurement. And Bob has a state, but Bob does not know what is the state. Not only does not know the state, because since also Alice does not know the state, but he does not know if the state that is received is correct or not. Okay? Now, the point is that at this point, Alice send a classical communication, so call on the phone, send an email, whatever you want, to Bob saying, look, I made a measurement and I obtained this result. Before to go further, so what is the probability for all the different measurements? The probability, this is extremely interesting because the probability that you realize a particular measurement, psi plus, psi minus, or whatever, is that is equal to the modulus of these vectors, the square modulus of this vector. But the square modulus of these vectors is 1 times 1/4, because I have to do this. So the probability to obtain each single vectors are all the same. They are equal to 1/4. So no matter what is the state, the probability that Alice, making his measurement, realized one of the 4 of the state is exactly equal to 1/4. So, okay, now we have this, this structure. So the point is that Bob received a phone call from Alice, and Alice tell him, okay, the measurement that I made is phi plus. At this point, since also Bob knows this law, he can send, so does not need to do anything on the state. The state that the qubits that is in his own allowance is exactly the state. So there is the state that I want to transmit. On the other hand, if I realize phi minus, what I have to do? So the point is that at this point, Bob realized a sigma z operator to this state, alpha 0 minus the 1, and this gives exactly alpha 0. So again, Bob does not make any measurement, does not know anything about it. The only thing that he did was make an operation, a sigma z operation. And this is not induced by some of his measurement or something, but only from the result that is communicated by Alice. And the same thing if now we put if the measurement is psi plus, we obtain the state alpha 1 plus beta 0. And then Bob, if receive a communication that is the result obtained by Alice is psi plus, the thing that he do, he apply transformation of sigma x. And this again gives the right state. Then that one that before, okay. I think that, and then in the third case, the transformation, if I made correct, I have to check. Let me just 1 second. Yes. After alpha 1 minus beta 0. So in the last case, he made a transformation that is sigma z times sigma x. And then in this case, what I obtain exactly is. So the point is, without making any measurement, Bob obtained again the state that was given to Alice to be transmitted. So the important point is Alice make a measurement, but all the probability to obtain a result does not contain any information about the parameter of the state. So the result of the result of the measurement of Alice does not provide information on the state, does only provide information for Bob or which kind of unitary operation has to make. And Bob does not need to make any measurement. The interesting thing is you can see here from this expression that in this state, there is no anymore. And so when we realize the measurement, and we realize, since we have realizing a measurement, the state that we obtain is 5 plus 5 plus plus I minus plus 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 minus tensor alpha up alpha 0 plus beta 1. So after all these processes that we described, the state we obtain is separable. So we have used the entanglement that we have before. We destroyed completely the entanglement, and the result of this, this new state is a separable state. Because as you can see, every time I make the rotation, so I can put all the projector here and the same state. Okay, so the fact that entanglement is 0 after all this operation is a clear indication that we use entanglement as a resource. But okay, one can say, okay, this is only because you decide to do this kind of process. It's not really needed. Probably we don't need to use entanglement. This is only a casualty for your example, but there can be example in which the entanglement is preserved. I want to, okay, there is a more general proof of what we will see now, that's made by the Orodecki family some time ago. I don't want to enter in their analysis because it's extremely complex. But I want to show that if, to make an example, we imagine that Alice and Bob have a channel, the entanglement channel, but this entanglement channel is not perfect. The amount of entanglement is not exactly equal to 1. We want to show that the fidelity that we obtain is less than 1. So the state that we can send is not accurate. Let's try to make this example. So, yes. So now let us consider the case in which the channel that Alice and Bob has is something written in this way: lambda 0, 0 plus 1 minus lambda 1, 1. Obviously, if we take lambda equal to 1/2, we recover the case of before, and so we have this maximum entanglement state. If lambda instead is 0 or 1, do we have a state that are fully separable. So the channel is not entanglement at all. So now again, we want to send the state psi that is alpha 0 plus beta 1. So again, at the beginning, we have a state that is, that we can write like psi c is alpha lambda 0, 0, 0 plus alpha root of lambda 0, 1, 1 plus alpha square root, just 1 second. Alpha square root of lambda, no, 1 minus lambda, 0, 1, 1. Plus beta per root of lambda 1, 0, 0 plus beta per root of 1 minus lambda 1. Now, again, do the same stuff before. We will write 0, 0, 1, these two qubits, the state of these two qubits in terms of the best state. And the state again is alpha square root of lambda over square root of 2 p plus p minus 0 plus alpha 1 minus lambda over square root of 2 psi plus psi minus plus beta square root of lambda square root of 2 this is psi plus minus psi minus plus beta 1 minus lambda, and then this is over square root of 2 with pi plus minus pi minus times 1. Let me times 1 times 0. Okay. Again, so it is, let me put 1 square root of 2 just in front because it's useless to bring everywhere. We have 1 square root of 2. And then we have pi plus alpha square root of lambda plus beta square root of 1 minus lambda plus minus we have alpha square root of lambda minus beta square root of 1 minus lambda plus psi plus beta square root of, just 1 second. Just 1 second is state, I'm forgetting the states, 0, 1, and then psi plus, we have beta square root of lambda 0 plus alpha square root of 1 minus lambda 1 minus lambda 1, and then again the last one is psi minus beta square root of lambda 0 minus alpha square root of 1 minus lambda 1. So, like as you can see, while before we had the state that is realized on B after on Bob after the measurement, they are not anymore the right state. So it's not more something that is alpha for a vector plus beta for a vector, but all these coefficients are weighted for lambda 1 minus lambda. So square root of lambda, square root of 1 minus lambda. So the point is that, again, now imagine that you don't care, you say, okay, let's try to do our job, our best. In the case in which you measure, so in the case in which Alice realized a measurement, they will obtain the eigenvalues associated to phi plus, the state is this one, and since for the table we said before, Bob does not make any change. So the state that we obtain is alpha square root of lambda plus beta square root of 1 minus lambda. 0, 1. I'm forgetting always the state. If we made this other operation, if we realize phi minus, what happens is that we obtain alpha lambda times the state 0 minus beta square root of 1 minus lambda times the state 1. But in this case, we have to make a sigma z operator. And so the transformation becomes alpha, so this minus becomes a plus. And so it becomes exactly the same state over here. So in both the two cases in which we have phi plus and phi minus, the state that we obtain is the same. On the contrary, if you do the same stuff for psi plus, and then you have to take into account for phi plus, you have to take sigma x, so you have to change, you obtain something that is alpha square root of 1 minus lambda 0 plus beta square root of lambda 1, and exactly the same you obtain when you obtain as a measurement psi minus, and then you made sigma x, sigma z transformation. So we can write this one as psi plus so at the beginning, one thing that you can immediately see is that no matter what happens, the state that you send to your friends is corrupted, because it depends on the value of lambda. Is lambda exactly equal to 1/2, we recover the state of the previous case, the ideal case. But as soon as lambda is not equal to 1/2, your results start to the state. At the beginning, they are different. So you can send this one, you can receive this one or this one in a random way. Not only these are different, but also the point is that they depend strictly on lambda. So if lambda is very close to 1/2, we can say, okay, it's not a huge problem. But if lambda is 1/4 or something like this, actually the state that you send and the state that your friends will receive is completely different. What does it mean that is different? What does it mean that is very different and not so different? So try to make it try to make a measurement of this difference. The idea is to use the fidelity. The fidelity can be written as the trace of the state that we obtain times the state we want to, the density matrix of the state that we want to send. Now, we have so we have to evaluate this quantity when the density of the state that we obtain is the sum of these two terms. This state obviously we have to do the matrix. And let me just 1 second. So we have here we have alpha square, so 0, 0 with lambda plus alpha square times 1 minus lambda the density matrix 0, 0 plus linear x beta square lambda plus beta square 1 minus lambda 1, 1, and then we have the mixed terms, then alpha beta, alpha beta star 0, 1, and this is lambda times 1 minus lambda, and plus beta alpha star 1, 0 times lambda 1 minus lambda. So this is the density matrix that we obtain after the measurement on the state on Bob. And now we want to ask, what is this quantity? If this quantity is equal to 1, the fidelity is perfect. So if the fidelity is less, this quantity is less than 1, the fidelity is not perfect. It is the difference between 1 and the fidelity, say how much is the error that you make. Okay, obviously this lambda, this can be simply written like alpha square. This also is beta square, nothing else. So when our state psi is equal to alpha square plus alpha square to 0, 0 plus beta square 1, 1 plus alpha beta star 0, 1 plus beta alpha star 1, 0. So if you want, and then if you make the trace, so if you do the product and make the trace, what you obtain is that the fidelity is equal to the product of these two terms, that is alpha to the fourth, the product of these two terms, that is beta to the fourth, the product of this term with this term, because 1, 1 then becomes 0, 0, and then trace this contribution, that is square root of plus lambda 1 minus lambda alpha square beta square, and this plus again lambda 1 minus lambda alpha square beta square. Okay, that seems quite tricky, but can be easily evaluated. alpha square, beta square. Beta square, beta square. So now, what is the idea is that when we have alpha square, beta square, we can we have that since alpha square plus beta square is equal to 1, then we have alpha square plus beta square. The square is still equal to 1, but this is equal to alpha to the 4th plus beta to the 4th plus 2 alpha beta, alpha square, beta square equal to 1. Then this brings the fact that alpha to the 4th plus beta to the 4th is equal to 1 minus 2 alpha square beta square. So we can substitute this stuff here. Then with the fidelity it becomes 1 minus 2 times alpha square beta square, 1 minus square root lambda minus lambda. If I haven't made any mistake. Not totally sure, but I think that the result is correct. Now the point is, okay, this is a quantity. This quantity depends on the state, depends on the characteristic of the channel, so how good is the entanglement, depends on different things. But obviously, our problem is that one of the main requests of the quantum teleportation is that we can provide some results, but without knowing what is the state. So we don't want to have any information about alpha and beta here. The point, the only thing that we can do then at this point is to average over all possible alpha and beta. That's so this can be done. It's a little bit long. I don't want to enter the detail, but simply believe me that the average of alpha square beta square, so beta is equal to 1/6. So you can, so the average fidelity is equal to 1 minus 1/3, 1 minus, no, there is something that does not sound. There is a mistake somewhere. Just 1 second. Check. There is. No, it's correct. Just 1 second. There is a mistake. I have to find where I put. 1 minus 1/3 is correct. Oh, I forgot here. There is a 2. It's because there are 2 different contributions. Sorry. Okay, that is now it's much better. In fact, when because what happened? So yeah, that too. Yes. When now lambda is equal to 1/2, we have 1/2, yes. Just because so 1/3 because is 1/3 here, 2 minus 2/3. Yeah, okay, that is. Sorry, made a couple of mistakes. Yeah, because this is correct now, because when lambda is equal to 1/2, 1/2 of 1/2 is 1/4, square root is 1/2, 2 over 2 is 1, so 2 minus 1 is 1, and that this gives the right correction, the right measure for the entangled state. On the contrary, when you consider lambda is equal to 0, you obtain 1 minus 2/3 is the right measure. Okay. Okay, this is tell us that when the channel is not ideal, the fidelity is not maximum, and there is the limit case when there is no entanglement at all. The result is equal to 2/3, and this means that you can, in some way, realize a sort of quantum teleportation also with classical channel, but the result is not deterministic. So you can try to make some observation on Alice, send to Bob the communication. Bob can reconstruct the state, but the result that they obtain is not ideal, and the fidelity will be never be equal to 1. If the fidelity of teleportation is greater than 2/3, what you obtain is the measure, the measure, the system, there is for sure there is entanglement inside the teleportation channel. Okay, now we have to move to the Bell inequalities. Probably it will be perfect to do a small break here. Okay. I made a mistake here. Programmazione mi uccide. Can we start? Okay. Okay, so quantum teleportation, as we see, is based on the fact that we are using the resource of entanglement. Do you hear me on the? Do you hear me? Hope so. Only check if there is any problem.
Sì, si sente.
Oh, ok, perfetto. Okay, so we have seen that the fact that there is entanglement can be used as a resource to realize quantum teleportation has many other important quantum information process. The point is that, especially at the beginning of quantum mechanics, people really does not believe as entanglement was something, something correct. The people really believe that it was a sort of a problem of the theory. So, especially in the 30 and 40, when with the Copenhagen interpretation, the concept based on entanglement and this kind of state that we already written, that seems to be non-local, seems to violate all the physics that we know up to that time. And a lot of people start to think about quantum mechanics as an effective theory, not a real theory. Say, it provides the correct experimental result, but probably there will be a more complex theory, completely local, completely perfect, that gives the same kind of result. And what we see is only the fact that we are using this effective theory, with which the results that are coherent with what we see, what we know up to that time, we have to keep, and all the rest we have to discard. And there was this discussion involved a lot of super important researchers like Einstein, Schrödinger, and so. And the point was that so the idea of Einstein and all the other people that does not believe in the correctness of the quantum quantum theory was that to be so. Imagine that you have two observers again, Alice and Bob. That Alice and Bob have two different quantum measures. And then this quantum measure can have, each one of that have a set of possible results. Leader. A and B, let me say it like this. So the point is that the probability, so up to them, the idea of that the probability of to obtain result A and B, observing making the measurement along A, B, capital A, capital B, is equal to the integral of a sort of hidden variable, set of hidden variables lambda, distributed with the probability lambda of the probability to obtain A as measure A when the hidden variable assume a value of lambda, same times the probability to obtain B, observing B, when the fixed value of the result is again lambda. So they believe that this is the correct way to obtain the measure. The problem is that up to them, this probability can be extremely complex. You don't know exactly what it is. These are hidden variables. You don't know exactly what are these values. Say, okay, we don't know. we can use all the quantum mechanical tricks to make to obtain our result, but keep in mind that the correct way to express everything is one. And these, for it be more than 30 years, 31, 32, yeah, 31. This approach seems difficult to answer because there was a claim that since this approach gives, if you do correctly all the experiment, give the same result of the quantum mechanics, you have no way to discriminate between the two results, the two approach, the two theory. The point is that this problem was overcome in the 60s by Bell, that find a way to obtain an inequality that that can be violated only by quantum system, but not from classical one. Then this started a huge work of analysis about this inequality. There were so at the beginning there was the Bell inequality. Then there other people discovered other set of inequalities. Some of them are more interesting for some reason. Some were more easy to be checked from an experimental point of view. So there were there is before it was only one inequality, the Bell inequality. Now we speak about a family of inequalities, the Bell inequalities, and then today we will we analyze one particular inequality that is called the GH-SH, coming from the name of the authors that don't ask me to remember, Clauser, Horne, Shimon-Hildt, that are the four people that write down this inequality. That, again, exactly as the Bell inequality, they provide a limit, a threshold that classical system cannot overcome, and that instead quantum system can work. Let us analyze. So suppose again, and now that just 1 second. Suppose now that Alice and Bob has two set of operators. Okay. Two sets of operators. So Alice has operator A0 for A1 and A2. And Bob has two set operator B1 and B2. To make the things easier, let us imagine that all these operators can give you only two different results, or +1 or -1. So if I observe A1, I can obtain +1 or -1. If I obtain A2, +1 or -1, the same things for the B1 and B2. Again, A1 and A2 can be realized on Alice on his system, subsystem. Let us imagine his qubit. B1, B2 can be realized by Bob on his subsystem. That, again, for simplicity, let us consider the qubit. Now, the idea of the CHE, so let us write this quantity S, that is equal to the expectation value of A1 B1 plus the expectation value of A1 B2 plus the expectation value of A2 B1 minus, this minus is fundamental, the expectation value of A2 B2. Now, let us imagine, okay, let's now at the beginning, we will try to make a prediction of what happens for a classical system. So in agreement with the hidden variables approach that we see just 1 second before, and then we will see what happens in a quantum system. Let's start with the classical system. Now let us suppose that Alice and Bob realize this experiment, and they obtain, so suppose that for there is a classical system, there is a particular value of lambda of this set of hidden variables, and then we have that the results are A1 of lambda, A2 of lambda, A1 as a result of A1, of capital A1, A2 as a result of capital A2, B1 as a result of capital B1, and B2 as a result of capital B2. So now, if we go and write this here, what they obtain in this case is nothing else that S is equal to, for this particular value of lambda, we have A1 of lambda, B1 of lambda, plus A1 of lambda, B2 of lambda, plus A2 of lambda, B1 of lambda minus A2 of lambda, B2 of lambda. Now, we can do some small trick on this stuff. So we can collect A1, and we have A1 lambda, B1 lambda, plus B2 lambda, plus A2 lambda, B1 lambda minus. Now, we have said that the operator A1, A2, B1, and B2 can only admit two different values. So when we have here B1 lambda and B2 lambda, we have two possibilities. Or they are the same, or they are opposite. If they are opposite, this term goes to 0, and this term gives something. If they are the same, this one goes to 0, and this gives this something. So let us consider two cases. Let us consider at the beginning that they are opposite. So if they are opposite, this term goes to 0. So we are here, so we can say A2 lambda is equal to, so if we go to the modulus of S, that is become 2 lambda modulus of 2 times B1 lambda. But as we say, A1 and A2, also B1 and B2, they are limited between 1 and minus 1. So these terms, this modulus here is 1, this modulus here is 1. This term is equal to 2. Same stuff happens instead if they are the same. This one goes to 0. This quantity is equal to or plus 2 or minus 2. So when we take the modulus, is equal to 2. So we have A1, 2 times A1, B1. And then this again, this gives you 2. So the point is that obviously this is for a particular choice of lambda. And we have to make an average of all possible value of the hidden variables. So what we have to say that the quantity S is equal to the integrals over lambda of the quantity S di lambda. If we consider the modulus, we have modulus of S has to be equal to the modulus, the integral, lambda, S lambda. And then for the triangular properties, this is less or equal of the integral of the lambda. P di lambda, we have to consider the modulus, but since P is the probability, is always positive, so it's useless to put the modulus. Modulus of S of lambda, but this is equal integral of the lambda times 2. That is, since this is the integral of all possible value of lambda over probability, this integral is equal to 1. So this is equal to 2. So we have that this quantity, the modulus of the inequality, if it is considered for a classical system, that's less or equal to 2. So, okay, this is a clear value. Then now we want to check if it's possible for a system that obeys to quantum mechanics to violate this quantity. If it is possible to violate this quantity, then it means that there will be some kind of observables that one can try to make and check if the system of quantum mechanics are the system that describes the physics of the universe, or they are only a trick that to make better the evaluation. So again, let's come back to our beloved state. So let's come back to our best state, 1 square root of 2, 0, 0, plus 1, 1. And now, to make an example, let's put the Talis as choose as operator A1, operator sigma z, and choose the operator A2, the operator sigma x. Instead, Bob chooses operator sigma z plus sigma x over square root of 2, and chooses B2 sigma z minus sigma x over square root of 2. And then we can make the observation. So let's try to evaluate this quantity. So let's try to evaluate A1, B1. This means that we want to evaluate the expectation value of this state psi, the state, the operator that is 1 square root of 2, sigma z over A, sigma z plus sigma x on B psi. Okay, this is equal to 1 square root of 2, I want to forget, psi sigma z A sigma z B psi plus psi sigma z A sigma x B. Okay, when we consider this one, this means that the state 0, 0 goes in 0, 0. So this is give the contribution equal to 1. 1, 1 again goes to 1, 1. Contribution equal to 1. Then we normalize for the 1 square root of 2. And then we obtain that has to go to the square because we obtain 1 square root of 2 from both the two parts. This one will give a contribution that is equal to 1. So this is 1 square root of 2, 1 plus. Instead, this one gives a contribution 0. This is simple because sigma z, so if apply sigma z A sigma x B to the state 0, 0, it goes to 0, 1. but 0, 1 is not present in this state, so the expectation value is 0. Same stuff happened when I applied on 1, 1, goes to 1, 0. So this contribution is 0. So the contribution of this correlation function is exactly 1 or square root of 2. Oh. Then the same things we have to do for all the other terms. Also, I try to go a little bit faster. So for A1, B2, the only difference here that we have a minus, but the minus here does not have any role, because obviously the same term sigma z still give me 1, but the term sigma z sigma x still give me 0. 0 or minus 0 is exactly the same thing. So also that one, these are the second terms, give me 1 or square root of 2. Then we have A2, B1, that is instead the expectation value. This will be do. So 1 square root of 2 pi, and then we have here sigma x a plus sigma z b plus sigma x a sigma x b xz xxx I, that is 1 square root of 2 pi sigma x a sigma z b pi plus pi sigma x a sigma x b psi. Okay. So again, now we want to evaluate this quantity. This quantity is as before. When we have 1 sigma x, 1 sigma z, we have a change of the 2 qubit, but not for the rest. So when you start from 0, 0, we go or in 1, 0 or in 0, 1. But no matter if you go in 1, 0 and 0, 1, is not present in the initial state. Distribution is 0. So this term does not give you any result. Instead, xx gives a result, because when I apply on 0, 0 goes to 1, 1, and when it goes to 1, 1, and when I apply to 1, 1 goes to 0, 0. So I have contribution 2, then I normalize for 1/2. So again, this means contribution 1 or square root of 2. And then there is the tricky point of this inequality is that now we have to consider A2, B2. The difference from B1, B2, that here there is a minus inside. And the trick, the result, so the approach is exactly the same. So we have a minus here. There is a minus, a contribution of 1, but we have minus 1 or square root of 2. But in the inequality, there is a minus. So when we consider S is equal exactly to 4 times 1 or square root of 2. Or if you prefer, yes, if you prefer is 2 over square root of 2. That is greater than 2. So the idea is that if we have a quantum system, if our system is quantum, and we can realize a set of operations. This is only an example. That we can consider different examples. For example, for an idea, you can start to think about rotation of this operation, because in some way you can see A1, A2 as a sort of axis in which you have to consider, and then this can be considered a sort of rotation of 45 degrees, but you can consider a different kind of rotation, which we have, instead we have square root of 2, that this is nothing else than the cosine of 45 degrees. You can consider a cosine of another angle and the sine of another angle. So you can do a little bit of a trick, and then you can see that this value stay always the same. You can, for all pure state that are entangled, no matter how much are the entanglement, all these inequality violate, so for any set of operator, except for operators that are trivial, so for example, operator in which A1 is sigma Z, A2 is minus sigma Z, that is no problem. So for all this set of non-trivial operator, you violate the inequality. So at this point, what we are saying, it seems that non-locality is entanglement. So what I'm saying now is that if I have entanglement, I can define a set of operator, and if I define a set of operators, I can violate the inequality, and then I can check this inequality. So in some way, it seems that we are saying the same. We are looking at the same property in a different way. For pure state, it's true. So if a state is entangled, you can find a set of operators, and this set of operators violate the inequalities. The inequality is the GHSH inequality, or all the other inequalities that you want to find out in the. As soon as the state is not pure, this is not true. It's possible to prove it in a general way. It's a nightmare. And you need to enter in light theory. I made once, and it is a nightmare. So let us do it with an example. Let's show that exists entangled state for which that does not violate the GH-SH inequality. And for this reason, you can find a hidden theory that can describe this kind of state. So again, we have always consider our beloved state that is our state C, that is 1 square root of 2, 0, 0, plus 1, 1. And then let us consider a mixed state derived from the state, that is a state rho that is equal to P C plus 1 minus P, the identity operator divided by 4. So with the probability P, the state is on this particular base state, or the probability 1 minus P is whatever you want. Now, let's try to evaluate at the beginning this point. Again, we choose always the same kind of operator. A1 is equal to sigma z. A2 is equal to sigma x. B1 is equal to sigma z plus sigma x over square root of 2, and B2 is equal to sigma z plus sigma x minus sigma x over square root of 2. Now, we can do all the evaluation step by step, but there is a trick. So when we have to evaluate this quantity, we have to evaluate the quantity. For example, let's start from the first one. We evaluate the quantity that is the trace of rho times A1, B1. But rho, as we say, can be written in this way. So this is the trace over P psi psi A1 plus the trace over 1 minus P over 4 identity A1B1. But as you can see, both A1, B1 are traceless, are operations in which if you evaluate the trace of sigma z or of this combination are traceless. Since are traceless, this quantity is 0. So the contribution of this quantity is 0. But this is not only for A1, B1, but is also equal for A1, B2, for A2, B1, and O2, B2. So the point is that the inequality is controlled only by this quantity. That is nothing else that the probability P or the expectation value of the operator A1, B1 in this case over the state C. That is, again, equal to P times 1 of square root of 2. So this is valid for this, is valid for the second, for the third, and for the fourth. So S, in our case, is nothing else than P times 4 over 2. That is P times 2 square root of 2. So, as you can, so the inequality say that this quantity to be to need a quantum description that has to be greater or equal to 2. So we can simplify. So P must be P square root of 2 must be equal to greater or equal to 1, and so P must be greater or equal to 1 of square root of 2. So if P is less than 1 of square root of 2, you can find a set of classical correlations, so correlation that can be written in terms of hidden variables that satisfy all possible correlations that you realize. Okay, you say, okay, interesting, but is this state entanglement and non-entanglement? Is entangled or entangled? Yeah, we can evaluate it. So the point that up to now we always look to the entanglement for pure state and not for mixed one. As we already say yesterday, entanglement for mixed state is a mess, but there are a few exceptions. One of the few exceptions is the case in which we have two qubits, like the case that we are considering right now, for which we can evaluate the concurrence. So evaluating the concurrence is a long process. So to prove it that concurrence is a measure of entanglement is a nightmare, even worse. But even evaluation of the concurrence is relatively long. So you have to take the density matrix rho. You have to write down density matrix that in which you substitute all the elements with the complex conjugate, not to make the Hermitian operation, but the complex conjugate. Then you have to evaluate the matrix that is sigma epsilon, sigma y A, sigma y B, sigma y A, sigma y B. Once to evaluate this matrix, let me call this rho tilde, then you have to find the eigenvalues of the matrix R, that is matrix rho tilde, and then you take the square of the eigenvalues of this matrix R, and then you write down that the concurrence is equal to the max of between 0 and the square root of lambda 1 minus square root of lambda max minus the sum 2 times root lambda max minus the sum over I that goes from 1 to 4 of lambda I. That is you can see it's a little bit tricky. It's not impossible. You can do it, but it's a long process. We will spend at least 1 hour doing this at board. That is useless. The important point is that, believe me, and I checked it before, is that in our case, this concurrence is equal to the max between 0 and 3 minus 1. So 3p minus 1 over 2. The point, what is? The point is that what is the value of p for which we start to become entangled? So when this quantity becomes exactly equal to 0. So when 3p minus 1 is equal to 0. That means p is equal to 1/3. But p equal to 1/3 is smaller than p equal to 1 square root of 2. So we have a situation for this state, this is Werner state, in which you have 3 different regimes. So p goes to 0 to p goes to 1/3. The state has no entanglement and cannot be can be described with hidden variables, approach hidden variables. From p equal 1/3 to p equal 1 square root of 2, the state is entangled, but still you can describe all the correlation using a model based on hidden variables. And then from p equal 1 square root of 2 to p1, p equal 1. In this case, you have both the two properties. The system cannot be described with local variables, local hidden variables, and the state entanglement. So this is important because this that we show as a particular situation, this is something that is true in general. So while for pure state, a state that is entangled never admit a description based on local variables, for mixed state, the situation is much more tricky. You can have a situation in which you have the entanglement, but still the correlation function can be described by through a description based on local hidden variables. So in a way that is completely in agreement with the classical mechanics. This is also extremely important because let me just add something. I think that we have. Let me see if we have some time. Yeah, something very, very fast. So also no locality can be seen as a quantum resource, but it is strange. So it's different from entanglement, coherence that we already seen, and magic that we will see tomorrow. Why? Because coherence, entanglement, and also magic are property of state. So you have a state, and then you have you can have a free state, and you can have a free operation acting on a state. Instead, the elements of a quantum resource for no locality is not the state, are the correlations. So you are not. So what are the objects of the quantum resource? Are directly the set of correlation. If the set of correlation can be described with a model with local hidden variables, then this set of state can be considered classic. And instead, non-locality as a resource characterizes the state, so the set of correlation that cannot be seen and cannot be described with the local hidden variables model. Again, to create a resource theory, even for non-locality, we always need the same ingredient. The first ingredient, what are the free state? The free state will be the state that you can describe with correlation PA, B, like the integral of the probability over lambda, the lambda, E, A lambda, probability to obtain B, observing the operator B, when the lambda is. So if you have this one, these are, you have a set of if you have a set of correlation that satisfy this this relation, then this set correlation is your free state, and you, transformation that let the free state in free state are stated in which you have only a reshuffling of the order of the set of operators, in which you make pre-processing or post-processing or measurement. All this process left non-local set of correlation in non-local set of correlation. And this wire entanglement is fundamental for a process like quantum, like for example, quantum teleportation, quantum sensing. For the non-local property, the non-locality resource is fundamental for code, for dense code, for quantum cryptography, because there is a process, so they use the process to in which violating the quantum cryptographic code means that you immediately start to be your system becomes local and satisfy the GH-SH inequality. So you immediately can track it back that there is a violation of the code. And then I think that okay, it's close to the 5 p.m. So I think that we can stop here for now, and tomorrow we can restart with the magic. Is something strange to say, but okay. Sorry?
Did you say anything about Discord?
Discord, the quantum Discord. Yes, I have to evaluate. I think that you have. Okay, obviously Discord. No, so no, I think that. So I have to make evaluation. So obviously I'm not sure. Discord usually is base-dependent property. I think once I worked with Discord, but I think that if P is different from 0, you can have Discord different from 0. So yes, for all way long. But if you want, we can make it. So it's not difficult, but don't want to say something that is wrong.
Question. Is there, you know, if there's any intuition to the formula for the concurrence there? The one.
So okay, the basic explanation. So if you look to the proof that is made by Wouters in his second paper, so the idea is that he tried to take it. So when he have a state, he tried to project a state on a different 4 different base states, where 4 different base states are the 4 states that we have seen before. Again, 0, 0. the state 5 plus or minus that are 0, 0 plus or minus 1, 1. I'm forgetting the normalization factor to go faster. Obviously, it does not work really on this 4 state. It works on the rotation of the state. So you consider all possible rotation, local rotation. So where this U is equal to U1 times. So you find the decomposition on the state, and then you find the best angles to have this decomposition, where the best means that because it takes the projection that is larger, that is this lambda max, minus the 3 lambda 1, minus the other 3.
You find the local rotation.
You take this as a basis. Then you find all. So this is a 4-dimensional. Okay, imagine that is 3-dimensional basis because it's difficult to go on the 4th. Then you find the best rotation which you maximize this inequality. And in this case, you can prove it that this is the best decomposition that you can have to. So or even better. The best decomposition that minimizes the amount of entanglement that you need to describe the state. But the proof is absurd, to be honest. Yeah. No, it's this is so. He wrote down 2 PRL for proving this formula. The first one in 1998. In which he considered only the case in which there are of this set of lambda, only 2 are different from 0, other 2 are 0. In this case, you can prove it that you are considering only, so your best decomposition is made only by 2 states. And then he was able to prove it. That one can be followed quite easily. And there you understand, okay, that's our W state, you decompose in W state or something. On the contrary, when in the year after, he generalized to the case in which you have all possible lambda different from 0, it's to be honest, it's extremely complex. And yeah, but the idea is always this, because the point is that you have to project your state in the possible of the state and find a way that maximizes this.
Another one. So can you develop a resource theory based on behaviors? Operations. You said before that resource theory of locality is harder because locality is defining of behavior. Right?
Yes.
Can you define the resource theory based on the quantities rather than the state?
So theoretically, yeah. Look, theoretically, you can define resource theory on whatever you want. You have only to define 3 things. At first, you have to define what is your free state. So something that is free, that has no trace of what you want. What is your resource that you want to define? Second, you have to find operation that bring this quantity. So this one state that are on the free set in another state on the free set. So you cannot use this free operation to bring outside. And then you have to check that this set operation that brings free state on the free state applied on another state, a different state, does not increase the amount of resource. Once that you have this one, you can. So theoretically, you can define, yes, on each. Yeah. That's depend on what you do about. So for example, Discord, you can define Discord as a quantum resource, exactly as a coherence. In fact, at a certain point, I was, when I was preparing this set of lesson, I was in doubt if I have to put quantum coherence, quantum Discord, as a first example.
Is there a simple way to write a local hidden variable model? Like you said, that you can have entangled states that are still meet a local hidden variable model. What is the local hidden variable model?
You can, okay, that's, I never entered too much, so, but you can really So since there is since your inequality is satisfied, because with that level of entanglement, this quantity S is less or equal to 2, then you can define a set probability. Then I never tried, but in general, once that you does not violate this quantity, you can.
I'm wondering if there is always a procedure to actually.
About that. No, sorry, about that could be that there is, only that I don't know. That is not.
Less than to imply a negative variable model?
No, it's proven that there is. So you can define. And to be honest, for what I understood, if you do not saturate the inequality, then there is an infinite number of models. He said if it's exactly equal to 2, then there is only one. Or one plus or other one as a way relabeling the option background, but nothing changed. He said if they are less than 2, there are FMA. An infinite number of variants. That is proved. There are theorems that are proved.